About 2 weeks ago, I made a video on two different texts on differential equations. The first one is entitled Principles of Differential Equations. Principles of Differential and Integral Equations. And it's written by Corduneanu, a Romanian mathematician. And the other book is by Bauer and Nohel. It's, I guess, called also Introduction to Differential Equations. You can check out the video here, it's on the channel. A viewer of the channel, Mr. Allen of Atlanta, wrote here down in the comment section a few questions about my video. He says, it's interesting, but what are differential equations? How are these equations used? And also, you mentioned that the first book is more theoretical than the second book, actually. What is the determinant factor between these two fields and their significance? You also stated that tables written in the second book are not your cup of tea, but in some cases aren't equations derived from the repeated formation of numerical data from the tables? So he goes on to say that he needs a little more information. So hopefully this video will be, a nice way to answer those questions. I recently had the chance to organize, all the textbooks down here, and I just, realized that I have a ton of books on differential equations, actually. So the textbook I was talking about is the Introduction to Differential Equations with Applications by Bauer and Nohel. And the other textbook is the book by Corduneanu. And this one is a beautiful, beautiful text, actually. We have basically two kinds of differential equations, ODEs, or ordinary differential equations, and PDEs, or partial differential equations, okay? So typically, students learn, the basics of ordinary differential equations in a undergraduate second year university class, okay? So during a whole term, actually. And PDE is a little more advanced. You require a little calculus here. So let's suppose you have a function y equal f of x, okay? Where f actually belongs in Cn of a certain domain, omega, and let's suppose that omega is a real subset, okay? Open real subset. So f is differentiable. Now, again, this is just roughly speaking, okay? So f in Cn means that y prime, which is, okay, y prime is dy dx, okay? So actually the derivative of y double prime, which is d2y dx2, all the way up to y nth derivative, which is dny dxn. This is the nth derivative of y. All these functions actually are continuous on omega, okay? So a differential equation, an ordinary differential equation, forget about the PDEs, right? So an ordinary differential equation is an expression that involves actually x and y in a few of its derivatives. So y prime, well, it could be all of them, y double prime, all the way up to y nth derivative, actually. It's an expression, an algebraic expression of this form. So, for example, for example, in high school, okay, you learned how to solve the quadratic equation. So x squared plus 3x plus, say, 2 equal to 0. So how to solve this thing? Well, remember, you need two numbers whose product be 2 and whose addition is 3. So those numbers are, of course, 2 and 1, right? So x plus 2, x plus 1 equal to 0. 2 times 1 is 2, 2 plus 1 is 3. Thus, if the product of these two things is 0, that means that either this one is 0 or that one is 0. So x equal -2 or x equal -1, and then you solve the equation, meaning that when you plug back in these numbers into the equation, what you get is an identity here, okay? Now, what's a differential equation? Well, it's some sort of similar expression, okay? Except that it's gonna involve actually x, the function y, and one or more derivatives of the function. One of the simpler cases would be y prime equal to 0, okay? So this means find me a function y such that its derivative be equal to 0. Well, of course, we know that constants, right? The derivative of a constant is equal to 0. So the solution to this super simple differential equation is y equal a constant, any constant, real constant, okay? So for example, you can try to solve y prime plus y equal to 0. So we might think about the exponential or negative exponential of x, right? Or a constant times the exponential of negative x. So we know that y prime in this case, right, would be c exponential of negative x times, by the chain rule, the derivative of negative x, which is -1. So y prime plus y is equal to 0. Okay, so this function, see, it's a function over the real line, actually solves this equation down here. And so on. So this expression here, E, is an algebraic expression or non-algebraic, okay? So there may be a transcendental relation among these arguments down here, okay? Now, most of the differential equations are non-solvable, okay? So in a typical, second university year plan, you start out by taking, by solving separable equations, okay? Would look like y prime equal d of x times, say, h of y. So you separated here x and y, x from y actually, okay? So there's a specific method, super simple, to solve this kind of equations. Then you would move on to solving the linear equation. So what's a linear equation? Well, y prime plus a certain p of x times y equal to 0, okay? So when the right hand side is equal to 0, the equation is called homogeneous. When it's not, when you have here a function depending on x, right, then the equation is called non-homogeneous, okay? You would move on to solve the exact ODEs, right? ODEs, exact differential equations. So something like m of x y d y plus n of x y dx equal to 0. So I'm not talking, well, that's for another video, but how to solve these equations. I'm not trying to explain to you how to solve them. I'm just trying to explain the concept here. All right. The way to solve this is by checking whether there's a function phi, which depends on x and y, which is a constant actually, such that, differentiation, so d of phi be equal to m dy plus n dx. Okay, so if you could find phi satisfying, which is a constant, satisfying phi, a function of x and y, satisfying the equation in this precise sense, then you solve the equation actually, okay? And so on. Then from exact ordinary differential equations, you would move to on to solve second order ODEs, and then nth order ODEs, and then systems. And then what I like doing here is like proving the theorem of existence and unicity. It's a beautiful topic actually. Well, hopefully I answered the question. Roughly speaking, this is an ordinary differential equation. Okay, it's an expression that involves the function x and one or more derivatives. So the next question is, aren't equations derived from the repeated formation of numerical data from tables? I have no idea about that. I have little idea about history in general. I'm very ignorant about history, and I believe that was indeed the case, right? Theoretical concepts actually were developed after repeating an experience over and over and over again in the lab. As to whether tables themselves, right, were a pre-existing condition to differential equations, like here's a table down here, I have no idea. I have no idea. What I certainly know is that the value of the theoretical side of differential equations is huge in science. I believe that mathematics is so much, but so much farther ahead than any other science actually. So much more developed, and I think mathematics is not only a science, but it's an art, an attitude toward precision, and toward this desire of doing things the way they are supposed to be. And myself, in my own case, well, I couldn't do anything other than pure mathematics. I mean, I tried to work in a bank. It didn't work. I just hated it. I'm an engineer myself. I'm a civil engineer, but I was never happy with engineering, with the engineers as well. So I like the fact that pure mathematics has nothing to do with nature. Thanks so much for watching, and apologies for the long video. Thanks so much, and see you in the next one.